Welcome back to Goliath. Today we're going to be going over another new reference design, and I'm here with Chris Wilson. Welcome, Chris. What are we working on here today? What's new in the world of reference designs?
Yeah, new year, new reference design. We're
Right.
we're working on a industrial IoT vibration monitor. It's targeted towards predictive maintenance applications for rotating industrial machinery. So you can think of things like motors and turbines, anything with like a rotating shaft in an industrial facility. This reference design will allow you to take vibration and temperature measurements of that piece of machinery and send that data back to the Goliath cloud.
Yeah, and we're using very modern and efficient methods to talk to a very old industrial standard as well, too. So all this is built on top of Modbus. What is Modbus?
Yeah, so Modbus is a pretty old industrial protocol. I think it's about 40 years old at this point, and it is a protocol that was designed originally for kind of communicating between PLCs in a factory. It can be used over different types of links, so you can run Modbus as a protocol over Ethernet. You can also run it over an RS-485 serial bus, and that's what we're using today. We have a industrial vibration and temperature sensor that has a Modbus RTU RS-485 interface, and we're connecting that to the Aludel prototyping platform that we've used in our other reference designs to talk to that Modbus sensor, pull back the data from the sensor, and then send that up to the Goliath cloud over a cellular LTE connection.
Yeah, I think one of the best things about like a protocol like Modbus or really any of the protocols that are out there is the standardization. It's not perfectly standardized. There actually is variation between different types of sensors, but the actual communication method to talk down each of these sensors and query what's on them and what's going on with them is Modbus, right?
Yeah, that's correct. So this reference design, we're specifically using a Modbus vibration sensor from a company called Banner Engineering. But Modbus in general is a pretty kind of generic and flexible protocol. The idea is that you can basically read and write either single bits. They call those either a coil which is a read and write bit, or a discrete input, which is a read bit. And then you can also read and write kind of chunks of bits, 16 bits at a time. They call those registers. And so there's input registers and holding registers that you can read on the device. And those are typically what contains the sensor data. So in the case of the Banner sensor that we're using, the holding registers contain things like the temperature, the vibration measurements in the different axes, things like acceleration and velocity components of the vibration that we're measuring. So all of that is stored in those registers, and then we're just reading those registers from the firmware side.
Right. And it's not a small amount of readings either. Like I was really surprised when you started showing me this, like just the number of things that are popping out of this sensor. Whereas I'd expect like, maybe you'd get one reading, or, if it's the most simple case of just like reading a resistor or some other like temperature monitor. It's just like just that one thing. But now it's like, no, you get every way that we're possibly storing this inside of this device. Can we take a look at maybe like what it starts to look like as well, so people get an idea of what the device looks like?
Yeah, sure. So we can take a look here. This is a picture showing on the right-hand side is the Aludel prototyping platform that we've been using for all of our kind of internal reference design prototypes here at Goliath. And then we have an M12 cable that comes out of the box and interfaces to an M12 connector on the Banner sensor. And that cable is what's used for the RS-485 electrical interface between the two. And then the Modbus protocol is layered on top of that.
Awesome. Okay. And then the Banner sensor is actually stuck to like a large servo or motor or something like that.
Exactly, yeah. So there's some kind of mounting holes on the Banner sensor that allow you to mount that directly to the chassis for a motor or a turbine, and it will sit there kind of measuring the vibration signature of that machine over time.
Great. And so what do some of these measurements look like? What is someone is a maintenance technician working on a large scale motor or something like it? What are they looking at when they're looking at charts and seeing all these various vibrations happening?
Yeah, so maybe it's worth kind of taking a step back and talking about kind of the maintenance strategies that these folks would typically be using. So there's kind of your more traditional preventative maintenance that a maintenance operation team would be using, which is you can kind of think of it like how you periodically service an airline, an airplane in like the airline
Touchy subject these
industries.
days. Yeah, yeah. They say when we're recording in 2024, maybe a car. How about a
Or
oil change on a car?
that's a better example. Yeah. So you periodically take in your car to get an oil
Yeah,
change every certain number of miles or every certain amount
right,
of time, whether or not that car really actually needs that
right.
maintenance.
Yeah,
But you do it because you don't want the car to fail in the middle of the highway out in the middle of nowhere.
right.
So that's
You
your
probably could
typical.
stretch it to 20,000 miles or whatever the equivalent is kilometers,
Right.
but you probably shouldn't because they say 5,000 or 10,000, whatever it is, right?
Right,
Yeah,
yeah. And so a lot of these industrial facilities are adopting what they call preventative maintenance strategies now, which is essentially using data from sensors that are attached to those machines to try and detect anomalies and figure out kind of predictions about when that machine might fail so that they can schedule a maintenance for the machine and do it at the most optimal time that doesn't cause an outage for the factory.
right.
And so
Exactly.
for this vibration sensor, typically what they would do is they would when the machine is installed and running normally, they would take a baseline measurement of the kind of natural vibration signature of that machine. And then as the machine continues to run, they would continuously compare the kind of running vibration signature of that machine against that baseline vibration signature. And doing that, you can detect all sorts of different issues like a bearing failure or like a rotor misalignment. All these different types of kind of failure modes of the machines can start to be detected by comparing these vibration signatures and doing this in real time with these industrial IoT monitoring solutions.
Right. Great. Great. So you're pulling the sensor data off of the device, then it's getting pushed up to the Goliath cloud. What does that look like when it hits the console?
Yeah, so we can take a look at the console here. So this is the Goliath console where we've got a project here for the vibration monitors, and right now we're looking at the LightDB Stream tab, which is Goliath's time series database, and we're seeing a bunch of sensor measurements coming in from the vibration sensor over time, and if we expand these out, we can actually start to take a look at what the data is. So we're seeing temperature data coming in Celsius and Fahrenheit. And then we have two different axes of vibration measurement. We have the x-axis and the z-axis, depending on how the sensor is oriented on the machine. And then we have different components of the vibration for each of these axes. So we have acceleration components and velocity components. For acceleration, we can see things like the peak acceleration, the RMS acceleration, kurtosis and crest factor. And then for velocity, we can see the peak and RMS velocity components
Yeah.
of that
This is
vibration.
starting to get,
So,
yeah, it's just seeing all of the different things that are here. Yeah, it's
yeah,
not a small amount of data. So
yeah.
I
And
feel
so
like
you,
a motor expert might know what they're looking for. But ultimately, an IoT system like this, anyways, it's really about getting that data up to the cloud, sending it to your data teams, and then putting it
exactly.
in front of the people that are the motor experts or the predictive maintenance experts.
Yeah, exactly. Like when I first started this reference design, I had no idea what any of this data meant.
Yeah,
But
right.
when you actually start graphing it, you can pretty quickly see what a kind of baseline looks like versus a kind of unnatural kind of anomaly looks like in this data, because you see
Mhm.
kind of a flat line for the data and then a spike when something weird happens.
Got it.
Um,
Got it. And so you are charting this as well?
yeah, so we built a Grafana dashboard. I've got a sensor here on my desk that is measuring the temperature and vibration data, and right now it's just sitting there. These charts are kind of zoomed in, which is why this looks pretty spiky.
Mm.
But
Yeah.
we can actually, I have a little kind of fake vibration motor here that I can turn on, and we should be able to see in about 10 seconds here. When the next measurements are sent, you can see a spike in the
Oh my.
charts,
Yeah.
and
Yeah.
so you can pretty obviously tell that there's something wrong with this machine
Got
when you
it.
start to see these giant spikes
Got
in
it.
the
So you're
data.
you basically turn on a kind of a artificial shaking, like if you're at a washing machine that was kind of off kilter or something like it, right? You'd be able to
Yeah.
monitor if it's doing something weird like that.
Yeah, I bought like a foot massage motor off of Amazon that I'm using
Nice.
for
Yeah, good job.
for testing this out here.
Yeah, that's great. That's great. Okay, cool. Well, so what does it take to actually build this sort of thing? So what does the kind of the system design look like
Yeah.
for this whole thing?
So if you we've got a project page here that if you go to projects.goliath.io, we have a detailed page that describes exactly how we built the reference design hardware. It's got some photos, and then it also has a block diagram that you can go and check out here. So if you look at this block diagram, you'll see that there's the Aludel base kind of carrier board that has a SparkFun ThingPlus NRF 9160 board, which provides the cellular connectivity, and then that's interfaced through the carrier board to two micro bus click sockets for microbus click boards. And in one of those sockets, we have an RS485 transceiver board that converts the UART from the SparkFun module into an RS485 interface. And that's what that M12 cable plugs into to interface to the banner sensor. The other thing worth noting here is that the banner sensor requires 24 volts to operate. And so we actually have a splitter combiner cable system that allows us to inject 24 volts to power the sensor. And then the Aludel prototyping board here just interfaces to the sensor via the RS485 interface and speaks Modbus to that.
Got it. Yeah, that's very common to have like kind of independent power supplies in an industrial context, like and especially 24 volts.
Yeah. So the banner sensor I think takes 12 to 36 or something. There's kind of a wide range of input voltages that you can use to power that.
Great. Okay. And then like you showed already, it's kind of pulls that data back. It's using Zephyr, the Goliath firmware SDK built on Zephyr that's targeted at the NRF 9160. You read all that stuff all the way back. You have this in the GitHub repository as well, so people could actually see how you're talking to the sensor, how you're pulling that into the Zephyr subsystem using there's a Modbus API. Is that right?
Yeah, that's correct. So we have all of the source code for this firmware is published on our GitHub page here. And like you said, we're using the Zephyr Modbus APIs to do all of the actual kind of underlying communication with the sensors. So if you're looking for an example of how to talk to a Modbus sensor or a Modbus node in Zephyr, this is a pretty easy example to follow. You can come in and check out the source code and figure out exactly how we built this reference design firmware.
That's great. And so if someone wants to, they get the firmware, they're like, yes, I'm ready to do this. How do they then build it themselves? What they can do to build this?
Yeah. So if you wanted to build this yourself, as we mentioned, what we've been showing so far is built on Goliath's internal prototyping platform, which is the Aludel platform, and you can't actually go out and buy that yourself.
Sorry, that's all for us. We keep it. Keep good stuff.
So we've been working on this program called the Follow Along Hardware program, which is essentially replicating these Goliath reference designs using off-the-shelf hardware. And if you go to the project page and you click on the NRF 9160 DK follow along guide, this will take you to a guide that will show you how to actually build this reference design yourself, but using all off-the-shelf hardware that you can purchase from DigiKey. So in this example, we have an NRF 9160 DK development kit from Nordic, and that has a little shield that adds 2 click headers to that development kit. And then we plug in the micro RS485 clickboard into that socket, and that essentially mimics the Aludel platform that we had been using to run the Zephyr firmware. And this page will go through exactly how to assemble this hardware yourself. So we give you a hardware block diagram for the follow along hardware. There's a parts list that shows you exactly which parts to go and buy and has links to all of those parts on DigiKey. And then the guide continues to showing you how to download and flash a pre-built binary onto this kit. So you don't
Yeah.
actually have to start by installing a Zephyr toolchain and compiling the binary yourself. You can just download a pre-built binary off of GitHub, flash it to the device, connect to the Goliath cloud, and start kind of playing around in the console just to get a sense for how the reference design works. And then once you're comfortable with that, you can go down to the bottom of this guide, and we provide a link to the README on GitHub, which has really detailed instructions about how to go through and actually set up a tool chain, how to build the firmware yourself, so how to actually compile the Zephyr firmware, and then how to flash that onto the device using the West meta tool that Zephyr provides.
Right. And that's when you could start to customize too. So say someone like wanted to take this, start building a product off it. That's great. Probably don't want just what Chris has done here, even though it's amazing work and it does everything on this sensor. You might want to add other stuff in, right? You might have another click header or whatever.
Yep.
Or because it's Modbus, you actually might move to a different sensor, right? That is actually one of the probably the most powerful things about this specific reference design is that it can be redeployed to another sensor by then going to then just pull that sensor's information off of it instead, right?
Yeah, and so actually it's really easy with the way that we even have the hardware set up here. There's an M12 connector interface. You could go buy any other Banner sensor that uses that same 5-pin M12 connector and speaks the Modbus protocol, and you can adapt the reference design to use, that type of a sensor. It could be a temperature sensor or any other kind of industrial sensor, or you could even just build your own sensor or buy another off-the-shelf sensor, plug it into the M12 interface, and then there's a couple lines of code that you would adapt to change, which holding registers you're reading off of that Modbus node.
That is super cool. Yeah, I think that's really the power of these kind of standardized protocols and being able to pull that stuff off. I always think about it like in terms of I2C or similar, right? You could like go and kind of query what's out there and as much as sensors that might be an I2C bus. However, I would never hang an I2C sensor out in an industrial environment, right? That's really where you want to move to something like Modbus, because it's got RS-45, which is more immune to noise, and it's just more noise. It's more protected against a lot of weird stuff that happens. Industrial environments are nasty.
Yeah, so. Yeah. All of this stuff is IP rated. I mean, you can tell, exactly. Even just all of these cables and sensors, that you can tell the quality is a really high quality, and that they're all sealed against dust and the rest of the environment. You pay for that. They're really expensive.
They are not cheap. Yes, industrial is not afraid to have a couple of extra digits in their price tag, but you're often paying for quality and usually really specific stuff too that's targeted at like not just anybody is monitoring a 100 200 horsepower motor or something like it, right? It's
right.
Like, yeah, it's very specific to high value industries. So.
Yeah, and you want it to be reliable. I mean, like you don't want to cheap out on the sensor that you're using and then have your motor obliterate itself.
Yeah, exactly. Yeah, it's much cheaper to spend a little bit on a sensor than a lot to replace a motor that just blew itself up. So,
yeah,
that's great. Well, Chris, this is a great reference design. I think it's very, very customizable towards a lot of different sensors that are out there. It's targeting a really interesting application space. You did mention there's one other thing that you have in the works that will be pushed into this reference design in the future as well.
Yeah, so we're also working on another feature that would allow you to use the RPC capability that Goliath provides. If I go back to the console here, we have a remote procedure call tab where you can actually put in a method that you want to call on the device. You can add parameters to that method, and then you can click call method. So in this case, we have a get network info method here that we can call, and that will provide us back some information about the network information of the device. Another feature that we're working on related to Modbus is the ability to actually make Modbus function calls through this RPC interface. So you could imagine having the ability to plug on a generic sensor and actually, read a coil or read a holding register on the device without having to write custom firmware to actually go and do that. So that's another capability that we're currently looking into and hope to have available in this reference design in the future.
Yeah, I really like that idea because that also then plays into like the idea that you could plug in, like you said, a generic sensor or just really any arbitrary sensor, play around, figure out what you want to do, what you want to talk to, what registers on there, but then you could customize your firmware on your host machine, upload that to the cloud, push an OTA, and now you just have a dedicated firmware for that plugged in device. And it really starts to open up a lot of possibilities there, I feel like.
Yep. And it's worth mentioning that you can also make these RPCs through the command line interface or the REST interface. It doesn't have to be through the web browser here.
Yeah. Yep. Yeah. So that's really opens up a lot of new opportunities and makes it even easier to pull in the wide range of sensors that are out there. And they're, like Chris is showing with this M12 connector, that one is specific to Banner, but just the generic plugging in, it's an A and B connection for RS-485, I think, right?
Yeah.
Those are the two wires.
Yep.
Yeah, and then you could just wire it up to the terminal blocks and away you go. So that's really pretty magical, I feel like.
Yeah.
Awesome. Well, great job, Chris. I'm really excited to see this out in the world, seeing people take advantage of it, building lots of new industrial things, making maintenance easier, making more efficient factories and machines, and improving the world with IoT. So thanks for designing this.
Yeah, sure.